Hi there, thanks for joining me for another episode of Draw, Make, and Code. I'm your host, Ed Cavett, and in this episode we're going to be making a stochastic generative system. So what is stochastics? Well, if it's new to you, it was new to me, but it's not new to the world. It's been around for a long time. It's just a fancy word that describes structure that has chaos in it, or trying to make something meaningful out of randomness or a system of randomness, which it kind of lends itself to computers. They're good at creating these things over and over again and using randomness to do it, and then you can ask questions about that randomness and get some structure to come out of it, which is what we're going to do here. In the description you can find a link to my GitHub, which will have this code included the way that you see it here. There's also a link to a browser page which will open the actual code, and then you can watch the program or you can look at the code that way and play around with it and have fun. And it's all fully annotated in something that mostly makes sense. There might be some spelling errors and maybe some grammatical errors there, but you know, it's a lot of information that you get for free. So what do you want? In this version of a stochastic system, we have a walker that draws a path from the left to the right, and as it changes directions or changes its movement, it leaves some kind of geometry, a circle, a square, or a triangle. This process repeats as it goes down the canvas, and then when it gets past the bottom, it goes back up to the top. And that's a global position. Tied to the global position that covers the whole canvas is a local position that covers just a strip of space that goes across the screen, and that's what's moving down. That's local position is tied to the global position that's moving down the screen. So we're kind of keeping track of two different Y positions, and one is relational to the other. So we're going to start with the blank sketch in this, and let me show you some slides first. Here we have how we decide which direction to move. So we're going to pick an integer, and then we're going to look at it and move a direction dependent upon which integer we're looking at. And you can have multiple conditions tied to each one of the direction types. So you could have like a 50% chance of moving an extra direction if it picks this one or that one. So you can get this variety. You get this discontinuity that happens so that there's sections of lines, so it's not all just one continuous line. You get these little breakups, like, or sentences of lines, or words of lines, I guess. The stochastics that we'll be using for this system comes from Perlin noise and a sine wave. So we're going to have a random determination to pick between the pseudo-randomness of Perlin noise or the structure of a sine wave. And then with Perlin noise, since it's a curved distribution, there's going to be invalid returns. So those we'll check for those, and if those happen, we'll just pick a random number. So it's going to be Perlin noise, or possibly just random, or a sine wave. So that gives it the pertaining to randomness. It gives you the structure and the chaos, which kind of defines stochastics. Next, let's look at how we're going to divide the canvas up into a scalable area so we can increase the fidelity of the output. So we can enlarge the canvas, and everything will be in proportion so that we can use that enlargement to create something like a poster versus like an 8x10. So we're taking fractions of the width and the height, and that's going to give us this little unit area. And then the steps are going to occur of that size. So if we move to the left or up or down, it's going to be the proportions of that unit area. And our geometries are also going to be a proportion of the unit area as well. It's also important to note that we're not translating to the center and using negatives and positives for our global position. We're just going to use the canvas's default origin, but our stripe is going to be coordinated with a negative and a positive, which will put it above where our location, our global location, or below our global location. and I'll be referring to that as the local X and Y. So global is going to be the canvas, and local is going to be our little stripe that goes across to create the path, the circuitous stochastic path. Let's start with the blank sketch in p5.js, and in the global space we're going to declare a variable that's going to hold our system. We're just going to call it shape. You can call it whatever you want, just so long as you're consistent throughout the code. Then we're going to create a function called setup, and that's standard for p5.js. Setup and draw are. So in setup we're going to create our canvas, and that's going to be the available window width and window height. Any geometries we draw inside that canvas, we want those to be centered. So we're going to find the center point of that geometry, and that's where it's going to go on the coordinates that we give it. We also want to start with a clean background, so we're going to put our background in setup, and then we're not going to do it in draw. We're going to do it in code again and diminish the background intermittently so that we can get this fading output over time. And also in setup we're going to declare a new instance of the shape by setting it equal to new shape maker, which that's what our function is called. Now we have another function in the global space called draw. Inside it we're going to do something really simple. We're just going to call a method inside the function that we're going to make coming up here, and that method is called update. In our function there are a lot of methods, not a lot, there are a few that handle the basic operations of what we need to do in order to make this happen. But all of that is going to be directed from this .update. So that's the important method, really important method. And then there's some other super important methods that come out of it. The ShapeMaker function is going to do all the business of creating the stochastics. It's going to output what you see here. It's going to check, make sure it's all in range. It's going to decide what it needs to draw, and it's going to actually draw it. So in the global space of the function, we have to declare some variables. We need one to hold the size of things, like I explained in the slide. We're going to take the width and we're just going to multiply it times a fraction, then that's going to give us our range that we're stepping by. And we're also going to use something called scale, which is going to be fixed, and then we're going to use something called shift, which is going to change. So if something is changing, we want to reference back to what it started as, we need the fixed variable for that. So there's kind of like a static variable that holds something, and then a dynamic variable that holds that same thing, but then that changes over time. So when you see that in the code, don't get confused. You're going to say, well, you're just duplicating things. It's like, yeah, but one of those things is going to be changing and the other one's going to stay the same. So that might confuse some people when they see it. It often confuses me when I see it in my own code. So I thought maybe if it does confuse you, I'd point that part out. As I'm going through this code, you can see it's pretty well annotated, and I kind of want to make this my format. I've been playing around with how to present this information in a way that covers the most people. And I really don't know how that works, because I know how I understand it, but I don't know how you understand it until you give me feedback, and then I can be like, okay, well I can do this, and maybe that will help out. So I thought annotating it in the video here would be kind of an extra step to help people understand what's happening, because I don't see that a lot in the tutorials that I've watched. So from our initial conditions, we're going to get where are we positioned to start. I have the output going down the screen. Now you, after you do this, or now, whichever you decide, you can just have it going down just one stripe of output. You don't have to have multiple stripes of output. That's going to be kind of the versatility of this. I think I started out with just one stripe, and then I added to it to make it go down the screen. And how I added to it was by adding this variable called this.shift, and then I just limited that, whatever that single stripe is already limited to that area, so all I have to do is just tie its location to that global location. So that's where in the slide you had the global location and the local location. works with that variable this.shift. We're also drawing a line from where we were to where we are, so we need to record our previous and current positions in two separate variables. I use XO out of tradition because in my brain that's the old X and the old Y. So that's kind of why it's just two variables there. I don't like to have a long variable name if it's something that I know in my head instinctively what it is. But if somebody else is going to be using this code, then they might have a problem with the really short abbreviated variables when you could use a whole word that says what it is. Lastly, here we have the movement type variable, this.d, and that's going to tell the system how to move. So we have this.update is going to do some output. It's going to output the line. But the geometry, the circle, the square, and the triangle, I'm going to send that to another method and perform all those actions in it just to keep things separated and looking nicer and easier to manage. I'm also going to have a method that handles the out of bounds if things are where they need to be, and if they aren't, let's put them somewhere. And then another method still for getting the movements. So we have a lot going on here inside this function, but we're going to start with update, and we'll branch out of update to those other methods, and then we'll make those other methods. So in this.update, let's figure out how we're going to pick our movement type. So we're going to use a random number that picks a 50-50 chance. So basically a coin flip of whether or not we're going to use Perl and noise, or we're going to use a sine wave. So I think I picked cosine. I mean, you can use sine, cosine, doesn't matter, either one. This is still going to return a -1 or a 1. So when I type this out here, I'm going to make a bit of a mistake in the parameters part of cosine because I copied the Perl and noise to make the second condition part, but I didn't change the parameters correctly. I will go back to that, so just keep in mind, if you see that, don't freak out. I'll fix it later, but for now we're just going to put this condition in here. Also, here's where we're doing the other methods. I'm just going to draw those out for you now so you can see what exactly they are. We have one that's going to produce our circle, square, and triangle because we have a lot of conditions and stuff inside those conditions, so it can get pretty stacked, so we can keep that separate and then throw it down the screen and we don't even have to look at it after it's been made. So that's what I'm kind of doing here. I'm doing it for the bounds, and I'm doing it for how we move too. So since this .d holds our movement type and it's in the global space of the function, we can use it anywhere in that function. So even inside another method we can use this variable. So I don't have to pass anything into these methods from inside the function because all the variables they're using have been covered in the very first part of the function where we set up our initial conditions. And here in the bounds method, it's going to be doing a lot of heavy lifting because in addition to making sure that things stay where they need to be, it has to reset conditions and reset things back up to the top, from the right to the left, and if you don't set all those conditions correctly, it's going to cause some problems, which it does when I test this at the end. So stay tuned at the end so you can see how I fix a couple of minor problems in here. In update, this is the meat and potatoes of what's going on here. Our whole stochastic system is based on how we pick our randomness. So I'm using a coin flip for determining whether or not we're going to use Perl and noise, which is this kind of systemic randomness, or cosine, which is not random at all, it's linear. So that's our structured form and our chaos tied together. And we're using randomness to pick between both of those, so you get even more randomness there. So this is really pertaining to randomness, but it's also controlled because we're moving from the left to the right, so we have this directional control. And we're also switching to a sine wave every once in a while so that we can get this back in the road and out of the weeds kind of feel to what the output is. It actually gives it this kind of melodic look. If you're not familiar with Perlin noise, I would invest some time in doing that, because even if you don't know a lot about it, you can get a lot out of it. But knowing how it works, you'll be able to get the most out of it. So take some time with that. If you are familiar with Perlin noise, in this example we're using three-dimensional Perlin noise, and we're tying the X and Y part to the actual X and Y of our object that we're moving around, and the Z part is tied to the frame count as just a simple incrementer, and we're multiplying that times fractions, so these decimals, so we get really small numbers, so we get small movements through the noise. Our interpolated range is going to be outside of what our range of integers are that we need to use to move stuff. The reason is because Perlin noise is a curved distribution. I don't want everything to be clustered in the center. I want to get a good amount of everything from 0 to 6, which I think that's our limit. But to do that, there's going to be invalid returns. There'll be negative numbers, there'll be positive numbers way over what we need. So when that happens, we're going to test and see, is it out of this range? If it is, let's just pick a random number. In the coin flip, if it's not Perlin noise, it's going to be the return of cosine or sine. And since I just copied the state from one condition in to do the else part, I just changed Perlin to cosine, but I didn't really change the parameters too much. In fact, I have too many parameters in this cosine. It just needs one. I'm going to go back and fix that later, but for now, just imagine that the parameters inside cosine, that's what it's supposed to be. The important part is the interpolated values, and that's the 0 to 6 in this case, because we don't get any outside, there's no marginal or outliers in cosine. It's either -1 to 1, so those perfectly interpolate to 0 or 6. Here's where we're checking the direction to see if it's out of bounds, and if it is, we're just going to set it to a random integer. And then now we need to keep track of, if we're going to change the X and the Y, let's store it first in XO and YO. So we're going to take the current position and we're going to put it into something that's now going to be the previous position. And that's how we can get our line drawn from one point to the other. We're going to go from a previous point to our current point. Instead of putting a whole bunch of code here, we can just call a method that will perform the operations of seeing how we're going to move. And it's going to look at this.d and then test that against a bunch of conditions and do what's inside those conditions if it's relevant. And then you can do some extra stuff in those conditions to make things that weren't relevant now relevant, so you get extra movements out of them. To do the color, I'm just going to set some math to a local variable. I think in this case I use green and red channels in RGB and adjust those a little bit with some randomness to get something between yellow and orange. And there's a lot of green in there, actually, it turns out. You can play around with that and get whatever colors you want to come out of it. Also, if you generate like a JPEG, you can put that into editing software and change the hues that way. So there's a lot of things that you can do depending on what your tasks are for this output. When we draw our line, we're going to put it in push and pop, so any changes to the stroke, weight, or any translations, rotations, anything like that is going to revert back to its initial state after we fall out of this pop. So everything's kind of contained. I like to do this because you don't have to worry about it, and it gives you a lot of control, but you have to be really thoughtful about it, because sometimes you can kind of hem yourself up not using the push and pop in a smart way, especially if you're jumping around and you've got a lot of conditions. It can get challenging, but here it's pretty simple, not too complicated. We're going to draw our line from the previous position to the current position. So that's our this.xo, yo to x and y. instead of putting all of the code to draw a circle or a square or a triangle, if this condition, we're going to put that in its own method, and then we can shoot that down the screen so we don't have to look at it once we make it. So it just helps us keep things clean. If you want to, you could put it in its own sketch, and in the index just refer to that sketch, and it will work that way as well. But if it's not a really long program and you don't mind scrolling back and forth, then just put it all on the same sketch. I guess it'll work. Once you take out the annotations, this program really isn't that long. It looks super long now because there's tons of text in it. So the first function method that we're going to start with is this.geom, which is short for geometries. It's making the geometries of the system. So we need a local variable set to the size of the system. But I skipped that part somehow. I end up scrolling up too far in my notes and skip that line. So you're not going to see that here, but it's critically important that we have that variable here. And if we don't, we're going to throw an error later on, which is going to tell us that we need it, which is really helpful in solving that problem. But it's best to not have the problem to begin with. So there is a line that we're skipping here. For now, let's just go to the line that you're actually seeing, and this is where the type is happening. Which one of these things do we want to draw? A circle, a square, or a triangle? We can do this stochastically as well. I'm doing it kind of linearly with the sine wave because everything is moving up and down and around, and it gets kind of clustered and overrun. You don't notice that it's a wave so much, but it allows the repetitions to kind of line up in ways that gives it this musical note kind of quality. So play around with that. You can put Perlin noise in there, you can put any number of things in there to get these different type values as a randomness. But in this case, I figured since there was so much randomness everywhere else, whatever piece I could use to make some structure would kind of limit it and make it more stochastic. So the procedures here are actually pretty simple. We're picking a value, we're going to look at that value. If it's equal, then we're going to do this. If it's equal to this, we're going to do this. So we have a circle, a rectangle, and a triangle. So that's 3 values to choose from, and hopefully we've limited that to 3. Oh no, there's a couple other geometries as well. I think I draw a square using lines, and I'll talk about that later on. But for now, let's just start with the simple stuff. We're going to start with the fill and the stroke. Let's randomly coin flip whether it's going to be like white stroke, black fill, black stroke, white fill. So we're going to use the inverse of one or the other. And you can make those colors, and that's what I do. Use some local variables again with some mapped to the X and Y for the 2 different colors, and that's going to give you some variety depending on where it's at on the screen. So I thought that would be kind of cool as well. To make things easier, when we draw our triangle, we're going to translate to the spot that we're at. So now 0, 0 is going to be that spot. So now we can just work around 0, 0 instead of having to subtract and add things. When we get to the conditions to do the geometries, the circle and the rectangle are pretty straightforward. We set our rec mode to center. So when we draw a triangle, we're working from the center, and when we draw our circle and square, we're working from the center as well. Well, the circle and square pretty much draw themselves. All we have to do is give them position and a size, and they're drawn. But when we get to our triangle, we kind of have to tell it where its points are, where the vertexes of this triangle is. To do that, and I'm kind of jumping ahead in the code because I think the circle's easy, the square's easy, you get it. If it's type 0, make it a circle. If it's type 1, make it a square. And if it's type 3, make it this triangle. So the triangle, we're going to move from our origin, we're going to move up. So that's going to be negative y value. And we don't have to move the x yet because that top point of the triangle is in the center. So that's our 0. So our first coordinate is pretty easy. It's going to be 0, comma, negative, whatever the size of our geometry is, and divided by 2 because we only want to go halfway up and halfway down, and then those 2 halfways make a whole way, right? And so we're dealing in divide by 2's. So when you get to triangle, you're going to see that there's a lot of divide by 2's. So the first coordinate is 0, comma, negative size divided by 2. Kind of easy to understand. And then we're going to move to the left, and we're going to go down from the center, from that origin. So now we're using a positive 1/2 for going down, and we're using negative 1/2 for going to the left. So that's where you get the negative size divided by 2, and then size divided by 2. And then our last coordinate is just moving over to the right. So you're changing it from a negative to a positive. So then it's size divided by 2 and size divided by 2. And then it's got all the vertices, it closes that shape and creates the triangle. So it's pretty easy if you break it down step by step. But if you don't know what is what in the triangle statement, you're going to have a confusing time with it. But once you break it down and kind of draw a picture and do some dividing lines and stuff, you can get a really good sense of how to make your triangle coordinates. Now the third and fourth type movement are squares, but they're not drawn with like a perimeter. They're drawn with a fill that's using intermittently drawn lines. So we're going to make a loop that goes from 0 to the size of our geometry, and we're going to skip so many positions along the way, and we're going to draw lines going from one side to the other. And this is going to create like up and down lines making a square, or horizontal lines making a square. And I thought that would be a little bit of a mix-up of just like a solid geometry. So when we do our lines for this, it's kind of like making the triangle, except for you just have 2 points instead of 3. And you're starting at the center of that geometry, so your left-hand point would just be negative 1/2 the size, and your right-hand point would be positive 1/2 the size. And same for the top and the bottom, except for you're using the y coordinates. So that's kind of how it breaks up here. We're using our loop for one of the coordinates, so y in one case, x in the other case, and whatever coordinate is in our loop, that's what is the other coordinate is going to be our fixed one. So it'll be our size divided by on the negative and our size divided by on the positive. So it's kind of not too hard to understand there, even though it looks kind of complicated. If you break it down in your brain, it's pretty easy concept to grasp. The next method is how we're going to move. So we're going to look at what our integer is, and then we're going to perform some action based on that integer. We need a simple condition for each one of our direction types or our movement types, and those are labeled 0 through, I think there's 6 of them, so 0 through 5. So just copy those many times because it's pretty much the same condition, just different insides. So in number 0, we're going to travel up, and then inside this condition we're going to put another condition that's going to be a coin flip whether or not we do some other movement. So we're going to move along y for sure, and then there's a coin flip of whether or not we move along x. And if we move along both of those coordinates at the same time, it creates a diagonal. There's a way that you could make the condition just draw like go 90 degrees off of the vertical line and make like an elbow piece. That's kind of what I was going for, but the way that I just changed the d value inside that condition, and then it falls through all those other conditions, and when it reaches the one that I've changed it to, then it's going to perform that one as well. So it's not just limited to performing one movement type per frame. It could perform multiple movement types. This is sensitive to the arrangement of those values. So let's say in condition number 2 here, I set d inside that condition equal to 0. Well, it's got to go through all those conditions, the frame has to flip to the next frame, and then it goes through the condition again in order to find that one. So it's not really, things can change in between there. So whatever movement type you want to access inside a condition, again, it has to follow in the flow. So if I change, say the condition for this.d equals 3 is true, inside that condition I can change this.d equals anything greater than 3, so 4, 5, or 6. But I can't change it to equal 0, 1, or 2 because it's not going to work right that way. Does that make sense? How the flow is really important to how we can mix directions of things inside a single condition. So that's going on a lot, but it can kind of limit you, and you have to be really particular about the order of the movements of directions. So I kind of worked on that a little bit. In the first iteration of this, I really didn't think about it too much, and when I tried to do what I just said I was doing in this program, it wasn't working right, so I had to reorganize things. So it's kind of a drawback to this method. I'm sure there's lots of different ways of doing it, but this is the way that I chose because it just sort of worked in my head the second time around. In a couple of these movements, I'm multiplying the size that I'm stepping by times something, like maybe 1/2 or whatever. And instead of producing a 45-degree angle like it would with 1/2 the step, or the full step is a 45-degree angle, 1/2 the step of any single coordinate, so like 1/2 the step of x or 1/2 the step of y, it's going to produce an angle that's not 45 degrees. So now you can get, just by changing the number you're multiplying by, you can get different angles of movement that go up or down. So you're not just fixed to the straight up, straight horizontal, and straight 45 positive or negative. So that's a little bit of variety there. In this get move method, it might seem like there's a lot of stuff in here, and there kind of is, but all that stuff's just like duplicates, and there's subtle changes inside each one of those. And whenever you have duplications in code, there's always a better way of doing it than duplicating things. So there are much better procedures for this, but those can get difficult to show others how to do. So that's why I did it this way, but I'm sure you could come up with something that's better once you're more familiar with how this is all put together. At the end there, you can add more conditions with more movements, just so long as you change the ranges up in the this.update method. So in bounds, we have to check to make sure things don't go out of range. And there are, I think, 3 things we're going to be checking. We're going to be checking the movement from left to right. So if it goes off the right-hand side of the canvas, we need to go back. We're also going to be checking for when these strips, as they move down, if it goes off the bottom of the canvas, then we need to set that strip, that global location, back to the top. So we're dealing with those changes. We also have a previous X and Y and a current X and Y, so we have to set those back to 0, or to where we need to restart to. And our Y's, we need to make sure that we fix that to how we're moving the stripe down the screen. So there's a little bit of complexity here, and I think I break it down in the annotations, but the this.xr is because when you're drawing the stripe, the local Y can go outside of the stripe area. And when it does, that's just kind of like outside of the canvas, so you want to put it back inside that stripe. And if you do that, in order for it to move out, it may have advanced the X. So if you just drop the Y back down to where it was and the X down to where it was inside the stripe, it's going to move away from the line that it kind of started. So it's going to have this discontinuity. In order to keep things a little bit more contiguous and have branches that come off of our drawing there, I set that X back. So if it does go off of the stripe, I want to go back to the previous X and down to the center of the stripe with the Y, and then draw and keep drawing that way. In order to do that, I need to have a variable, that this.xr. So that's going to remember the X and go back to it. That's something to go back to if I need to, if that condition occurs. We also need to set the local Y whenever we do go back to the stripe. We're always going to set it to the global Y, which is this dot shift. So this dot shift is shifting the position for Y down the canvas. So our local Y position is always going to be anchored to that global position. So we're almost done with this. There's a couple parts that I've omitted, I've forgotten. I got lost in my notes. So when I run this, it's not going to work, or the output is going to be not right. So I've got an error that breaks the program, and I have an error that doesn't break the program, but it doesn't print the right output. So one of those is a syntactic error, kind of a reference error actually. I'm missing a whole variable. So you can see here size is not defined, and size is an important variable here, but it's a local variable. So I need to assign a local variable called size to hold the size that we're working with in order for that to work, and other things. So once you go back up to the top of this Geom method, pop that size assignment in there, and that should work. So when I run it again, it sort of works, but things don't go, they're not staying in bounds. The stripe is going way out of bounds. So I need to check for the stripe. And that's this condition here. I think I'm putting it in. So it's going to look at where the global Y position is. It's going to see, am I so far above it? Am I so far below it? If I am, then let's jump back to where it is exactly. So that's kind of the condition and the assignments going on inside of that. I noticed when I was recording the narration for this video how I ended up deleting a bracket that was kind of important. Well, it's critically important. The program's not working. It's running, but the output is wrong because the code, the conditions I'm putting in here, I think they're in the wrong place. They're in the update function right now, the update method. So I need to move the bracket down. So there's 3 brackets at the end. What that's going to do is move those conditions up into the bounds method where they need to be, and then everything's going to work right after that. So this is the output you should have once the program has been typed in correctly and been given to you correctly. So I'm just taking out all the annotations right now, and you can see there is a lot of text in there. This is just so you can see what's there. You can kind of pause if you need to on whatever part so you can confirm that you've put things where they need to in case your output's not running right. Wow, that's kind of a long tutorial, and you're still here, so you must have enjoyed it. If you did, hit the like. If you haven't subscribed yet, please consider being a subscriber. I post videos like these fairly regularly. As the quality and the complexity of these projects go up, the frequency of those uploads, it's not going to be as much. But you are getting something pretty good for free, so I'd appreciate it if you would hit the subscribe and join me every time I upload. And that would help support the channel. Also, if there's something that wasn't clear for you, or if maybe I could present this in another way that would help you better, let me know in the comments. That feedback is immeasurable in helping me design a format that helps the most amount of people, because if you have this concern or question, chances are other people do as well. So be sure to comment, and I guess that's it for this one. Again, program links are in the description, and until next time, as always, thank you for watching, and take care.